So we're going to continue talking about alkenes here, and then we'll then the exam is on Thursday. Okay, so alkenes is not on it, so don't worry about alkenes. All right. The project exam gives you a good idea, but it's not the whole picture, because you gotta remember we talk a lot more reactions. So ethers and alcohols. So those other reactions. Converting alcohols to alkyl halides with those dinyl chloride, phosphorus tribromide, and then transformation of ethers, epoxides. Those are fair game. Okay, so use the homework to kind of brush up on that. All right, but the format's pretty much the same. Really no multiple choice, and so it's all like the first two exams. All right, but any general questions before we begin? No? All right. So let's recall. Last time I think we just talked about the product, right? We did the reaction, but we didn't talk about the mechanism. So here's the mechanism. Of hydroboration. So mechanism, step 1. All right, hydroboration is a weird molecule. Boron here does not have a full octet. All right, and then if we look at the periodic table, boron is actually less electronegative than hydrogen. Okay, so boron here has a partially positive charge. Hydrogen has a partially negative charge. All right, so boron here doesn't like electrons too much, okay? So here we have an empty p orbital. So let me remember that when we drew Lewis structures, that boron was an exception to the octet rule, okay? So what happens here is that here is a generic form of an alkene. All right, and what boron does, that boron, since it has no p orbitals, is going to form a complex to the double bond like that, okay? So when the boron and the hydrogen, when they add to this molecule, it's going to add to the same face, okay? So this is an example of a syn addition. So right here we can call this syn addition. Okay, so let's use our example we drew in class last time. So we have a tert-butyl group here. And now here is where the double bond is located. So here's our hydrogen, originally attached. Now one of the carbon bonds here is going to be partially broken in the transition state. So let's put a dash bond here. All right, now the boron is going to add to the least substituted side. So there's two reasons for this. One is that the boron prefers the least substituted side because of steric hindrance. All right, so look at this boron group. There's two hydrogens here. So these hydrogens might get in the way of the more bulkier side. So that's why the boron adds to the opposite side here. So it's going to be forming a bond to this carbon atom. One of the hydrogens is going to be partially broken because it's being donated. And this other hydrogen is being broken there. Okay, so this part for the N, that's our nucleophilic part. And for the boron, that's our electrophilic part right there. All right, so this mechanism is a little weird. You're going to form a square. So this bond is breaking to form a bond to boron. And this hydrogen bond right here is breaking to form a bond, a new CH bond to the carbon that was previously an alkene. Okay? All right. So what happens now is, if we draw the result of this step, we get a new hydrogen bond. So I'm going to draw that out. You don't have to draw it, but I'm going to draw it just for clarity. And here, now our groups here, you see they have been added to the same side of the double bond. So here we can see here they're on the same side. So syn addition. Whereas remember oxymercuration, they've added in an anti-fashion because of the intermediate. But in this intermediate, both groups are added at the same time. Okay, so that's why it's syn addition. Okay, so then this boron group can react with two more equivalents of the alkenes. So I'm going to draw the molecule here. Two more additions here of our alkene. CH, double bond CH2. So two more equivalents of that. So we repeat this process two more times. But we don't have to show the steps for that. That's not important because it's the same exact thing, okay? So what we get over here then is we're going to get 3 alkyl groups of my reacted alkene here. And so we have CH2, CH2. All right, and this is going to be bonded to my boron. So I have 3 of these groups now attached to my boron atom, okay? So that's the first step. So that's called hydroboration. All right, are there any questions on the steps? Yes, Elizabeth.
The boron still has the 2 hydrogens on it?
No, so now they all been added to different alkenes.
Okay.
So now there's 3 alkyl groups. So we could think of this boron like this. So let me just draw that out for you.
I see where you're going.
Okay, boron's here. And then we have, remember the CH2 alkyl groups. So what this reaction has done, all the boron's hydrogens have been donated. So you only need like a third of a mole of the boron reagent because it can react 3 times. So you have that one, that one, and that one. So we have 3 of these groups attached to the boron. So now that's our reagent there. Okay, so in this case, we can abbreviate these as R groups. So the R group here can be this group here, CH2, CH2, C, CH3, like that. Okay, so we can abbreviate it if we wanted to. All right, so that's the first step, hydroboration. So you added borane, BH2, across the double bond. And this can accommodate 3 groups of alkenes. So you can actually get 3 of those alkene groups substituted there. And the next step, oxidation. That's when we liberate the alkyl group from the boron. So it's 2 steps. Okay, are there any questions on this mechanism? All right, this mechanism, not too bad, it's fair. Not in this exam though, but final is fair. So there's 2 steps, boration and oxidation. Okay, any questions? Okay, let's go to the step 2, oxidation. So I'll just, right now we're at the generic step here, step 2. All right, so this is oxidation. So borane is pretty reduced, no oxygen atoms. So we have to get oxygen atoms into the boron and pretty much just swap the carbon groups, okay? All right, so the first step here is, remember our, what was the reagent in the second step? Does anyone remember? There's sodium hydroxide and water, but what's the oxidizing agent? Yes, hydrogen peroxide. So let's draw hydrogen peroxide. So hydrogen peroxide is a weird molecule, has an OO bond. So the weak OO bond is what makes it so reactive. All right, so the first step here, you can pretty much deprotonate every, so hydrogen peroxide is very acidic, so the first hydrogen comes off pretty easily with just hydroxide. So you get a generic acid-base reaction, okay? So H2O will form plus the conjugate base hydroperoxide anion. Okay. So this is the reactive intermediate. So now we're going to use this OOH minus and attack our boron reagent. All right, so I'm going to just draw out all the borons, all the alkyl groups, just so it's clear to see how it happens. So I'm going to create a new page now. So let's swipe this over. Okay. So the second step, let's redraw our boron reagent. So this might take a while. Let's just draw it. 1, 2. So guys, if you want to put R groups, that's totally fine. Just know what the R group is. But I'm not going to do that. Just so you can see how it's like this. But on a mechanism type question, if the R group is long like this, you can just denote it as R. Okay? You just specify what R is. All right, so the hydroperoxide is going to be in waiting here. It's going to come around, and it's going to attack the boron. All right, so boron does not like to be tetrahedral. That's why it usually has an empty orbital. It's not very stable. Okay, so when this happens, you get your intermediate. All right, oh, sorry. Let's draw out these bonds. So let's draw out the oxygen to the other oxygen. And then we could draw out the hydrogen too. All right, so this boron has a negative charge, but it won't last. Because under these conditions, it's going to spontaneously decompose, okay? So the R group here, I'll circle this R group. These electrons are going to migrate to this internal hydrogen. Oh, sorry. So the R group is going to do a rearrangement reaction and the rearrangement happens because this OO bond is very weak. The OO bond is very long, so that's very weak. It's very easy to cleave, okay? And that's exactly what happens. You cleave that bond there, like that. So this is called rearrangement. So this is like an alkyl rearrangement. So this would rearrange. And then what we have here is, so you're going to produce some OH minus. So OH minus is going to get like recycled as a byproduct right here. So it just goes back into the reaction to generate more hydrogen peroxide anion, okay? But what happens here is that this group, now it has been inserted into an oxygen atom. So now this is where the alcohol comes in. Like that. Okay. So, how many more times do you think this is going to happen? 2. Yeah, so 2 more times, okay? So let's draw an arrow here. And we're not going to write that, okay? You could just say, okay, here's another arrow. Every alkyl group now has been inserted with an oxygen atom. You don't have to show it 3 times, okay? 1 is enough. So you're going to get 2 more equivalents of OOH minus. All right, so you're going to get 2 more rearrangements. And so what you get now is a boron. Basically, all the boron atoms now, the boron atoms are has an oxygen in between the alkyl groups. All right, let's hopefully we have room here. So, I don't know if you guys know what borax is, but that's like a cleaning agent. It looks something like this. It's boric acid, a derivative of boric acid, okay? Oxygen atoms to be water soluble, and then the alkyl groups to dissolve the grease. Okay. So you get this intermediate, but now how does the alcohols form? Well, these reagents are very sensitive to hydration or hydrolysis. So hydroxide is going to come in. And it's going to attack the boron now. Okay. Now let's draw this group here. All right. So this group is going to be OH now. And remember, the boron has a negative charge. So boron with 3 groups, neutral. But if it has 4 groups, negatively charged. Okay? All right, so what happens here is that just one of these groups just falls off because this boron is unstable. So this is going to get replaced by OH groups because the OH group not really going to leave again. So the OH kind of forces all these alkyl groups to fall off. Okay? All right. So what we get here, let's just redraw it. All right. And then what we get here is this is our product. We want this. We don't want the borax. That could just get recycled or, to the waste. We don't want that. All right. Well, this will happen at least how many more times? 2. I'll show that in a separate step, okay? So now I want to show you what happened. What's the fate of these 2 molecules here? All right. So 2 things happen. Your alcohol is going to get protonated by what? What else is in solution that can donate a proton? Yes, H2O. So usually alcohols are slightly less acidic than water. So they're slightly basic. So this is a very basic oxygen atom, right? Negative charge. So it can just depronate water pretty easily. All right. So we regenerate hydroxide. So that's good because that's going to allow us to free up the other alcohol groups from the boron. Okay. And then, so that's the fate of this guy right here. So that's the fate of this one right here. Okay? Now let's talk about that boron, the other boron intermediate. Okay. So, two additional OH molecules, ions, are going to react with that boronic ester. Okay, so we have OH. Okay. So as well as with water. So this is going to cleave it and also protonate the alcohol. So we get 2 more molecules of our alcohol. And so this is called boric acid. All right. Well, boric acid is somewhat acidic, so you actually it doesn't stop there. So what happens here is that, let's see if I have some room here. Okay. Let's just point it this way. All right. So you have sodium hydroxide in the solution. So this boric acid actually doesn't stay like this. It becomes a good salt, sodium borate, Na3BO3. And this is water soluble, so you can just wash that salt out. And yeah, you can just recycle it after that. So that's the fate of boric acid. For mechanism, I really don't care if you show what happens to the boron or not. I just care how the alcohol gets produced. Yes?
So that's just like there's 3 AOH?
Yes. Yeah, to remove the 3 OHs, yeah. Right. Or, sorry, the 3 hydrogens to form water. Plus 3 H2O. All right, that's boration-oxidation. All right, let's do some examples. Okay, does anyone have any questions about the mechanism? So guys, be able to practice this mechanism. So when you see a problem that gives you an alkene and these reagents, you're like, okay, I should practice the mechanism and see if I can do that one. Okay, so let's do some examples before we move on. But any questions on the mechanisms? I know there's a lot of details, but if you practice this, practice makes perfect in these cases. All right, this new page. All right, let's do the simple one first. All right. Get in groups of 4. You're going to predict the product, and you're going to write. One of you guys is going to write the mechanism, and you're going to pass it to one other person, and they're going to check it. Okay. So get a sheet of paper. You're going to turn this in at 2 p.m. Okay, when I collect it. All right. Work on this for like 10 minutes, and then if there's any questions, we can go over it. Oh, yeah. Hold on. I'll be right back. Well, does anyone have a piece of paper? You can just share it and write all your names on it. Okay. So, guys, just submit one piece of paper for one submission. Just put all your names on it. All right, but I'll get some paper in case anyone needs it.
that boron is going to go to the least substituted side, which means the side with more H's on the outside. Just look at this one. This part doesn't have any.
Okay, so step one. I think
I'm trying to read this.
no, I know first one step three and one is from boron.
Yeah.
But it's gonna go. But I don't know
to
what
a
here.
hard boron.
Basically, they're all.
So the boron.
And then that's what. No, like basically it's like
Multiple times. So then
the height of the
because the first speech but this one is break. Very top.
Yeah.
Because the double bond is breaking.
Because I went to
Should
I do this thought and
Sure. Because the stage was right. So the husband is to this one. And then the base is and then hot we get that. And then for oxidation.
yeah.
So then that gives us hydroboration. So technically this is
I think the R is stage 2.
yeah. It's easier to erase. Okay, so then
We repeat
as medication is why we have oxide. So like what's first happening there?
Like,
is-
I understand, like,
for step two investigation, why we have that from the like this bond to the
Okay, the double bond is going
So
to boron.
well, no, I get why that, but why does the
So what's there? How does that
Wouldn't it just, cause look,
There?
I'm assuming these are CH3s, right?
That's okay. I just moved it out.
we have these
Okay, that bond is
Okay.
okay, and then the bond between boron and the hydrogen is going
basically so then the hydroxide will
right.
oh
wait, there was stage 2.
Okay, and then you're gonna draw this and they repeat two more
Cause
times.
like B 3 times,
or just like
the
do an
synthesis
arrow.
addition 3 times. So it should be
Hydrogen
one.
peroxide. Was that
Repeat times two, and then should I do
So
this?
boron.
That we write them here too.
like that?
Like you just want to project When you send me that, so just put B in the middle and
That's
that's
right.
so many.
Okay, we draw a lot and then we'll get to the rest.
So then
Oh, wait.
that's right.
So are we supposed to write this part?
Yeah, right,
Yeah,
right, and then we'll
because
put
like the
the
drink
drink
and
and
repeat, and then repeat.
Yeah.
Yeah, so
Like we get to the
shifted to
or the the H, the parentheses.
So
this becomes a solid line.
Right, so what's happening is it's doing this again with
Like that, and where's the double
the hydrogen, the other two hydrogens.
Okay.
That was correct, without, because I'm like operating the hydrogens go on this.
And then,
But, so this repeat two more times. Yes, then she has another.
Yeah, this one now makes a solid line. Now it's boron connects it.
Right, so it's this
it's like,
with solid lines, then minus the two.
Okay. And
Or
then this
after
double
the
bond's
one.
gone, right? This double bond is gone.
Boron with,
It's this one that you have right now.
oxygen.
Oh, that makes it
gonna be really long.
I didn't understand, they said.
So the boron's gonna have three of those.
The bottom one,
Just
right?
try to recreate it. Without the double
Without
bond.
the
Open it up.
Yeah.
Yeah, you're fine.
I'd say that drawing.
And then it's good. You
did that one right.
We could put an R.
No, you didn't.
Okay, we'll
You
get
didn't make that?
there.
Okay.
Today is my first
Like, what's this?
And then you're just gonna add the whole H, right?
And then we'll have it rearranged.
Those things more.
How do you know where to
Then we
connect?
get.
Like why can't you connect it from? So
I
this,
heard-
right here, like make another bond.
Technically, it should be to where the double is.
So what is it?
So we have to like turn it. Does that make sense?
Wait, okay, so
Or do you
then.
know how we have it attacked?
Yeah.
Part?
Oh, the most size
So it has to be on the same side.
bottom part.
Just rotate it and then you keep the
Always minus.
But then
Coming back
it's
right there.
Yeah.
I'm trying to figure it out. Does that go between the?
He was asking this thing with some more files.
Right. I'm just going to show like the flow. And then we have always minus.
And
Hydroxide comes in. And then eventually that must
oh, okay, like literally.
Yeah.
Okay. So part of me is the
It's like the initial.
So the Alkenes and CMA is like
That's more.
the top column.
The way you make it look like.
Yeah, just
There's
the
flash.
flat, yeah, there's no swaps, I think. So it's.
Yes.
Okay, R-E, very important.
No, I didn't like the.
So are you
water.
We just,
open?
we just added the.
We have to like add this to
Okay.
water.
The supplementing, we can.
Now, just a hydrogen.
Cause on here, he added this. Then our group, he added it.
So you did 3 cyclopentanes?
Yes.
So the H is boron? No, I think you're right, cause then if I should get added onto the graph.
We get,
Did you see how he added it 3 times?
Yeah, I did.
Yeah, that's what.
Oh, what is that extra hydrogen base? On which
So
one?
that you're adding.
I mean, he didn't really show like much of them on here. So we just kind of,
You're just trying to.
yeah, we just did the part for this part and then we're all deciding.
You understand?
What you guys got? You still working?
Yes.
Working hard, good.
Okay, then we get blue. Okay, attack boron. And now boron becomes negatively charged. Right?
And then that's gonna do.
This B that we have right here.
Okay.
So.
Right.
And then another rearrange?
It's gonna
Because the
rearrange
bond broke.
two more times.
Yeah, okay.
So
So
this is
water
just
comes in.
Rearrange.
This is what it looks like right now.
three. Yeah, that's one, right?
When you went for
This one?
Right.
let me draw the product.
Right, this is the view right
Oh,
over.
because then it's like.
Yeah, we haven't done
Here,
it.
I feel like I started.
I'm like super good.
I used to do that.
But then, can you show this? I don't know.
Up to this too.
Oh, so that's just. Okay.
If I were you, but you're not me.
You're working
I
on
would just
something.
do it like this.
Yeah.
Put these or these and then
I'm gonna nearly have be able to have 3 hours.
No, 3 hours?
Just like, this one's gonna jump on. Is it still gonna be like 3 or 3?
And then we that.
like, you know how 3 of these?
We get 3 of these. Like 1, 2, 3, 1 of these.
No.
So it's just to get our.
This is
That's bigger steps.
Yeah, I think I'm right.
I'm not down. It's great. I'm just questioning because I don't know.
They all have options.
Now.
Because we have 3.
I know, John says I didn't know.
It's neutral.
And then they are like each, but then it cannot so then you get really wash.
Okay.
No, it's I was trying to like, and I like self-love the idea of how I should stay home. Like, I was like, I'm like, why did you? I don't think that. I was like, I went through it. Like, I don't think it's too much going with it. And I'm like,
I was still in it. I was
I'm still in bed in my drawer. I'm like, and then she just starts doing shit like that. So I'm like,
That's a good one.
I'm just like, here.
now we have
You hold it like this, and then you click emoji to, and then you just like, hold it down.
Oh, okay.
I think my sister,
I'm like, this one.
Watch right there. No, remember the alkenes.
Okay, now.
This is not what the alkenes is. Yeah. Oh, wait, there. There's no two markers there. And that would just be a level. Remember, you can attack either face, right? So you can write receiving. If
So now we're all working on this, right?
so you can write receiving.
I like that because I can only get a.
And also work on the mechanism too. So your good idea. So the age goes
This
into more.
one is good. Have you seen this one?
That's wonderful.
So we're in this step.
I just barely saved. Or like this one.
Where is it?
Did you say?
Yeah, I'm telling you.
It's unstable.
That probably is all right.
One of our bonds is in
Okay.
Yeah, yeah.
What? Okay, and then it reacts with water.
Yeah. Good.
now.
It just walked through it really well though. I'm sorry.
Yeah.
Yeah.
Water.
Oh.
Yeah, I should say yeah.
Oh, it's not happening.
And then
So we need a
The double bond breaks, right?
And then I guess it would be like
Oh, wait.
three, and then
Yeah, think about the mechanism here. Boron, one of the H's goes to the more substitute side. Yeah, just don't forget about the arrows. So that's step one, right? So think about step two, which is the oxidation. You can skip it here. Well, you should show these arrows now. You should show that. And then you can just draw now the triselective and show how the bond breaks. So this is draw boron here.
I like the same thing to do right now.
Yeah.
But I
How long do you have to wait for it to dry?
All right, guys. You guys double check your work. What we get? So, where does the hydrogen go?
Goes to the bottom.
The bottom one? The top one, right? So you're going to get H here. And then you're going to get the OH over here. But what about the stereochemistry? Do we form one enantiomer or two? Two. So this is racemic. So this is the final product, okay? After everything's been done. All right, so that's what I'm looking for. And it will help you to predict the product if you draw the mechanism, okay? So I won't reproduce the mechanism, but it's very similar to the one I showed you. You do the formation of this, so you eventually get this, right? BH2, which eventually goes to B okay? So you eventually get this, right? And then the second step is oxidation. So I'll just make this an R group, okay? So the R group is so you get three of these R groups. The hydrogen peroxide, deprotonated, will come in and attack the boron. OH. Yeah, Catherine.
When deprotonate the hydrogen peroxide, where does that hydroxide come from?
Oh, the hydroxide from sodium hydroxide.
Okay.
Yeah. So H2O2.
We just have multiple of that, so yeah.
Yeah, so sodium hydroxide is what is the source of the hydroxide. So it comes in and deprotonates for you. Yeah. Yeah, so it's a mixture. So basic hydroxide will only work here. So here we have R attacking the first oxygen and breaking off hydroxide. So you get boron. Okay, but eventually what happens here, the boron will have 3 R groups. So eventually you'll get 3 OR groups. And if you just write OH minus here and just write the product, that's fine with me. Okay, so you get OR minus plus B, OR, OH, RO. Okay, and you repeat that again and again, and you eventually get all the alcohol. So you do this 3 more times or 2 more times. O minus, and then H2O. You'll get 3 equivalents of the alcohol. And then you'll get boric acid, Na3BO3. Okay? But you don't have to put that far. I just care about the alcohol. Okay? So if you don't want to balance it, don't worry about memorizing that part. Okay? But that's how it works in terms of everything being balanced. All right. So if you guys, any questions about that one? All right, we'll do one more example of hydroboration-oxidation when we get back. But if you're satisfied with your answer, everyone put their name on it, and volunteer someone, turn it in up here. Okay? And then we'll take a 10-minute break. Then we'll continue talking about alkene reactions. Okay? We're going to learn about a few more today. Thank you. Thanks.
Yeah.
Hey, Abby. Thank you. Thank you. So, what's this? So where's the handout? The left.
Did you get this?
No, it's online. Hold on. So this is what F. So you zoom in and go down the page. Scroll down. So you see your step one. So it looks like, so which atom is accepting electrons in the first step? The chromium, right? So your chromium is the electron file because it accepts electrons. And then which one's the next file? The atom, the oxygen, right? And the alcohol. Yeah, so you can say O atom with alcohol, which is the file. The electron file will be the chromium atom, chromium gas. Alcohol, yeah. So the chromium gas. That's the physics. Oh, the chromium gas in water. So it's up here. So that's the chromium gas there. That's the water. No, no, it's the H. Yeah. Because now that's accepting electrons, right? The alcohol. The equivalent is the oxygen on the water, right? See, it's donating electrons. No, they'll look at those ones. Look at this one. Yeah. So it's coming from where? The oxygen out on the water, right? Yeah. Hmm. water is being used to break a bond. So that has a specific name. That's called hydrolysis. So when water is used to make a bond, that's called hydro. Water lysis is like you sever a bond. So hydrolysis. Yeah.
Oh no, I think so too. When I was yeah.
I was thinking about I was really stressed out about that post style. It was so good.
No, we don't have time.
Okay.
Thursday's the exam. We don't have class next Thursday, and we don't have any. The week we get back, there's no class on Thursday either.
I
So
know.
there's no lab. Yeah.
We'll let us know tomorrow if I feel like
Oh, so that's final. That's the last day classes.
Yeah, Wednesday is the last day of class. Thursday is like the first day of finals.
Yeah.
So yeah, good thing our finals not that day.
When are we taking our final?
It's Tuesday. The 9th.
No, we're all vegetarian, so.
What is the yellow? I wanted to make a
Pecan pie. All right. Well, let's continue on. One thing I want to mention is you can get attack on either face of the alkene. So this is a racemic mixture. So I kind of drew that in there, but as long as you leave it as single bonds and no wedge or dash, you will tell me that's racemic, and that's the correct answer. Okay. So luckily, usually, unless you really need the specific enantiomer, you can just carry them both through the reaction and then focus on what enantiomer you need later on. All right, so let's do one more example, hydroboration. Are there any questions on this page? All right, so if you want to abbreviate it, I know these steps are long, feel free. Okay, just make sure you highlight what your abbreviation is right here, okay? All right, so let's do one more example of hydroboration-oxidation. So let's make a new page here. Remember how I said the boron preferentially adds to the less substituted side of the alkene? You can actually make that, you can actually push that even further if you have a bulky borane. So for example, I'm going to have a group that just has only one hydrogen atom. So I'm going to do an R2 borane. So the alkyl groups can be anything, okay? And instead of hydrogen, I'm going to put deuterium again. So let's put a deuterium atom there. So the same steps apply here. Hydrogen peroxide. All right, so very similar to the example we just did, but what's the only thing different? instead of a hydrogen, what we're going to put instead? Yeah, just a deuterium atom. All right. So there's two ways you can draw this. Let's say we're going from the bottom half of the alkene. So I'm going to make this methyl group come up. The deuterium is going to come out from the bottom. Now, where will the alcohol show up? Is it going to be trans to the deuterium or cis to the deuterium? Let's think. What kind of addition was it? Sin, right? So was that the same face or the opposite face? Same. So let's draw this wedged, okay? But what do we know about alkenes? They're symmetrical, right? So I can attack equally probability of attacking from the bottom, but also from the what? The top. So here we could write plus an enantiomer. So we're going to get the enantiomer too. So if you start with something that's not chiral, or that has zero optical activity, you're going to get a product that also has zero optical activity because the starting material is symmetrical. So it's symmetrical if we draw a plane of symmetry, draw all the horizontally, all the carbon atoms, okay? So this can also be represented using a chair. We can show that it's sin addition. So hopefully we didn't forget how to draw chairs. Methyl group. All right, so that's anti-Markovnikov selectivity. Okay, so there's one more reaction that will display this, and that has to do with radicals. So we're going to revisit radicals. Yeah, radicals will never go away. It's an important part of chemistry. They're always happening when there's oxygen's around, so in your body. So we could generate it too. Yeah. Tyler, any question?
Will this always produce an alcohol?
Yes. You don't have to worry. It will never. Well, if you use an let's see. Yeah, usually, unless it's intramolecular. So if it's intramolecular, you'll get an ether. So if you go back, well, not this one, but if it was intramolecular, I think it will give you an ether because you have now there's not a free oxygen atom, so it'll be cyclic. But I would say don't worry too much about those. Yeah, there are special cases. If anything, that'll be like a mechanism type question where you have to show me how it's formed. All right, reaction number 6. Anti-Markovnikov, radical reaction. So anti-Markovnikov. All right, so I'm going to highlight this. This is radical. Okay. So this is a radical addition. All right, so say we have our unsymmetrically substituted alkene, so non-symmetrical. All right, so if I add HBr, remember when we add HBr just by itself, it didn't do anything. Okay, but if you add HBr in the absence of water and in the presence of radical species, you'll get different selectivity. All right, so here we use organic peroxide. So R2O2 looks like hydrogen peroxide, but not the case. And if you shine this solution in light, you'll get anti-Markovnikov selectivity. All right, so where do you think the BR is going to go? If it's anti. Is it the side with more hydrogens on the alkene or less? Least what? All right, okay. Least substitute, yes. So you get this primary dis product. Okay. Now we have to make a little asterisk mark here. This only works with HBr. Okay? It does not work with HCl. So I'll show you the reaction with HCl. So let's compare this to HCl. So for some whatever reason, HCl does not work. So remember we have HCl, looks similar to HBr, R2O2, H nu. So we actually just get the expected addition from Markovnikov addition, so racemic. So this is simply Markovnikov addition. No radical selectivity. So this only works with bromine, the HBr. It doesn't work with HCl. All right, so you ever see the HCl version here, you're not going to do anti-Markovnikov. You'll have to write Markovnikov. It doesn't do the expected, what you expect it to do. Okay, so let's talk about this peroxide. So here's the mechanism. How does this work in a radical type mechanism? Okay, so the ROOR molecule are usually two species. So they're usually diterbutyl peroxide or benzoyl peroxide. Has anyone heard of benzoyl peroxide? They're usually in like skincare products to help your skin. So there's this molecule to help fight off, keep your skin healthy. So those are the R groups in the R2O2. So those are the species that are reacting. So we usually don't write these. We don't write them out because they, other than breaking the central bond, they don't really do anything else besides getting rid of a hydrogen or, forming the bromine radical. All right, for any radical reaction, what's the first step? Do you guys remember? Yeah, so what is that called? What kind of step is that? Initiation, propagation, or termination? Initiation, good. There you go. All right, so we're just going to abbreviate this as ROOR. So remember, this bond is the longest, it's the weakest, so when we shine light, we cleave it homolytically, so each atom gets one electron each. So we get two RO radicals, so oxygen center radicals, I guess more stable than carbon, but more electronegative, but they're still lacking the octet, so they're pretty reactive, okay? So that's initiation. So you generate the initial radical. Then step 2, you're going to use that radical. And it's going to react immediately with HBr. So HBr is also a pretty long bond, so not very strong. So it can get cleaved as well. Okay. So what would the product of this step be? Got RO what? H, so you form some alcohol. And what radical do you form? Bromide. So remember in in these reactions, we're propagating radicals. So we have one radical, and then we're forming another radical in the process. Okay. So when you have a radical reacting with something else that's not a radical, you're always going to generate a radical species at the end. Okay. So this Br then, we'll just keep that there. All right. So these are the initiation steps for the radicals. Now we're going to generate our carbon chain reaction. So that's called propagation. Remember, propagate the chain. All right. So now we get to react with the alkene. Okay. So which side do you think... Well, we know which side bromine's going to add, right? Which side is bromine going to add to? Which side? The least hindered? So the least substituted or the more substituted side of the alkene? Least. So we got to think about why that is, okay? So if we attack from this side, where does the radical end up at? The other carbon. Now imagine we have this, or, well, do I want to write that? No, let's see. All right, so this gives you, what if we attack the other side? What kind of radical would we form? So this one we form a secondary, right? But maybe we'll see it easier if we draw it, okay? So this is a secondary radical. So compared to a primary, which one is more stable? Yeah, so this one's more stable radical. So remember, guys, the selectivity in reaction is always dictated by the stability of the intermediate. So this is that one. Okay, so that's our first step. Okay, now let's compare that to... Oh, sorry, I guess it doesn't go down. All right, can you guys see that? It says this is more stable, right? More stable. Let's bring this one down. Doesn't matter? Okay, nope, doesn't matter. It's the iPad's fault. This doesn't work well with PCs. They don't want you guys to work well together. Okay, so let's imagine we attack the other side. All right, so I'm going to go to a new page. Does anyone have any questions about this? Well, I'll leave it up for a bit. So let's imagine we attack the other side. So bromine could add here, right? But where else could the bromine radical add? So we attack this side, right?
Right.
But theoretically speaking, we could attack this side too.
Right.
So let's see why that's not preferred, okay? So bromine radical. Oh, but where does this radical end up now? Yeah, the methyl, the primary position, right? So we compare the stability of the radicals. Which one is like leagues above, more stable? That one. So this is very less stable, okay? So the activation energy to get to this one is going to be much higher. So we don't observe this, not observed. So that's the reason why. It's the stability of the radicals. Okay? Now, the last step, let's go to the next, make a new page here. Okay? So the second propagation step is where this newly formed radical, all right, it needs to get a hydrogen from somewhere. Where would it get the hydrogen from? All right, so think about which hydrogen bond is the weakest. Is it the alcohol one or is it the HBr? Yeah, the HBr. So that's the longest bond. So we need to regenerate the bromine. So that's the only way we can. So this will combine with the bromine, HBr, and the radical will return to the bromine atom to now then recycle back. So here we regenerate the bromine radical. Regenerate bromine radical. And what can the bromine radical do again? Yeah, just repeat. It'll go attack the alkene again and form more product until eventually this process dies out. Okay? So one thing I want to mention here that this reaction also works to form different other products. So I'll put that right here. So reaction also works with diols. So instead of HBr, you can have this, RSH. Okay? RSH and phosphenes. Oops, sorry. Erase this. Put this in parentheses. My bad. All right, so phosphenes and diols could work, but this, however, sadly does not work with HCl or HI. We're not with so sadly it doesn't work with that, unfortunately. So there's no way to do this with HCl. We would have to figure out some other way to get HCl there. Okay. All right, so that's anti-Markovnikov of alkenes with HBr in the presence of radicals. Okay, are any questions on that example? All right, so the mechanism, it follows the radical one, and so it prefers the less substituted side because we generate the intermediate radical on the more stable on the more substituted carbon atom. Okay. Any other questions before we move on? All right, going to reaction 7 if no questions. All right, so I'm going to draw a line here. All right, so we talked about hydrohalogenation, but we didn't talk about halogenations in general. So here now we're going to talk about halogenations of alkenes. Anti-addition of halogens. So the thing about the radical one, we have a radical intermediate. So, and it's a planar alkene. So you get a mixture of stereochemistry if there is a stereoisomer. So not very stereospecific, but that's to be expected with radicals. They're not very stereospecific to begin with. Okay. But this one is stereospecific. Instead of syn addition, we get anti-addition. So let's imagine our alkene. We're looking at the alkene head on. So it has a dashed methyl group and a wedged methyl group on both sides. All right. So here we have bromine again, and here's our solvent, a nonpolar solvent, carbon tetrachloride, which sadly is becoming less and less available because of its effects on the global warming. All right, if I were to ask you this, what would you think the reaction would be? What type? Radical or just a regular reaction? You would think radical, right? But there's something not present there. What is that? Well, there's no heat or light. So that's your indication that it's radical versus not being radical. All right, so what you actually get is anti-addition of both the bromine atoms. So the bromine will add in an anti-fashion here.
Wait, just to clarify, if there's no heat or light, that's not radical.
Yes. Right. So radical usually requires a bond to be broken using light or heat first. Yeah. All right, I'll just write here, not radical reaction. So you're not forming any radicals here, okay? So what you get here is anti-addition. All right, so we got to talk about, like, how does this happen? Both our alkene is nonpolar and our bromine is nonpolar, remember? So why does the reaction happen anyway? So there's two things reactions happen by. They're either attracted by opposite charges, partial or full charges, or they have effective orbital overlap in their transition state. Okay, so let's talk about this mechanism. All right, does anyone still copy me down? You okay? All right, so let's go to a new page here. All right, so imagine your alkenes right here, right? So what kind of bond forms the double bond in an alkene? Is it a sigma bond or is it a pi bond? Pi bond. Remember, the pi bond has electron density above the double bond and below the axis of the double bond. So we can write things like this. All right. Now, what about our bromine? Our bromine bond is broken. So is our carbon-carbon double bond. All right. So the orbitals here, the bromine must have some effective overlap in the pi bond. So you see the shades of the bonds, they overlap, they match. So they're constructive overlap, okay? So here the lowest unoccupied molecular orbital, the LUMO. Remember, that's something that's high in energy, sigma star. So that's from my bromine bond. So that's my molecular orbital of Br2. So when I overlap that anti-bonding orbital, I'm breaking that bond, okay? And then I'm using these electrons from my pi bond to overlap with that, so I'm breaking my bond as well, okay? So here we can see there is substantial net overlap of orbitals. So there's net overlap, so the shading or the sign of the wave is good too. So this is what we call our HOMO, our highest occupied molecular orbital. And that is the pi MO of the alkene. Another thing we can say here that this orbital is electron rich. So when I have something electron rich, something electron poor, I'm going to get two new bonding orbitals that are ones that's much more stable and one that's much more higher in energy. And that's what happens here. That's why this reaction takes place. So what does the mechanism look like? So let's write the mechanism right here. So I drew you the orbital picture to give you an idea of what happens. Now this is the result. Okay. So it's a weird mechanism. So let's draw our bromine. Okay. So bromine is going to use some of this lone pair to attack one of the carbons. And then the alkene is going to attack back at the bromine atom and kick off this other bromine atom to give you a cyclic intermediate. All right, what does this intermediate remind you of? Yeah, epoxides. Remember we saw this with mercury? Same thing with bromine, all right? But in this case, the bromine, what charge does bromine have? Oh, one of them is negative, sorry. One of them is negative, right. What about the other one? Yeah, positive, good. So remember, there's this positive charge, right? So one side is going to be partially broken. One bond is partially broken in the transition state, like we saw with epoxides. But both of these are equally substituted, all right? But if they were not, since you have a Br plus sign there, Br will add Markovnikov type addition. So the more substituted carbon atom. But both of them are the same, so it's symmetrical, so it doesn't matter which one you attack, okay? So let's attack, remember, backside attack. So SN1 type, but SN2 type chemistry, and you break up the bond there. So what you get over here is trans addition. So the bromine is going to stick up here. But the bromine attacked from the bottom face, so that's why it's sticking out like this. So you get trans addition of the bromine atom. So see the bromines? What's the relationship between the bromines now? Anti-addition, right? So they're trans from each other in this situation, yeah. So they've added across the double bond in a trans fashion. All right. Let's do some examples and see if we can predict the product. Okay, so I'll do one example. All right, so we have cis-butene. All right, so Br2. All right. Okay. All right. So, what two products can we form? So let's so the key here is you're going to draw a line to indicate where the double bond is, right? And how you're going to arrange the bromines. Yeah, so my recommendation is you make one pointing down and one pointing up. Okay, if you do that, you can keep the stereochemistry the same because once you point something down, that will indicate the opposite enantiomer. Okay, or the opposite stereocenter. So let's keep the H pointed up here. But if you want to alternate the wedge and dash bonds, you can do that too. Okay, but you can't draw it down and switch the bonds because you'll just cancel out the stereochemistry switch. Okay, so you have to either draw the bromine coming down or draw it on the same side of the other bromine and switch to stereochemistry. Okay, but let me show you an example. So you see here, I kept all the wedges and dashes the same. But compare this example where we attacked, so this one we attacked at this position. So the bromine added in this position. Okay. So, all right, so I'm going to name this. See if you can assign the stereochemistry as, remember, practice 2R, 3R. 2, 3 dibromo. And what's the parent name? Yep, you're right. Butane. But what if I attack from the other side? Does that give me the same product? Let's see. So you also get this product too. All right. Now, instead of going up on the left, I'm going to go down bromine here. Bromine there. Okay. But I'm still going to keep the same stereochemistry to indicate that one stereocenter was attacked, but another one wasn't. All right. Are these the same molecule? It might look like it, right? But what if we try to flip it? What happens to the wedge and dash bonds? They flip. So are they the same molecule? No. They're what? Enantiomer. Yeah, but you got yes, S. Right. The enantiomer. So when we do the enantiomer, 2S, 3S. All right, so this time we attacked, the bromine attacked right here, okay? So what happens here is that what you get, well, let me just reiterate what we get here. We get the bromine intermediate. And then bromine can attack here. That gives you this product. But where else can the bromine attack? Oh, gosh. Okay. Which side? This side, right? Sorry, a little roundabout there. This gives you this product. Sorry, a little messy there. But you see where the bromine's attacking? It's always attacking opposite of the CBr bond. So that's why this red group here appears in the down position. And this group here appears in the down position. Because that's where the bromine added. All right, so you get anti-addition. So one thing we want to note here is you got anti-addition. But it's racemic. Why is it racemic? Yeah, so you can actually attack from the top face and the bottom face. But whichever one you attack, you're going to get these two enantiomers. So it doesn't matter. It's symmetrical too. So it doesn't matter which like if you form it doesn't matter if you form this one versus, think about this way. What if we did this one? Okay. So maybe if you want, if you can, think about what if you attack this group? Would you get the two same products on the bottom if the bromine is pointing downwards? The answer is yes. So see if you can convince yourself of that. All right, that's it. We'll do that a little bit early today. So that's it. We'll talk about more examples of this reaction on Thursday, okay? So study hard. Any last minute questions, let me know. The study guide is there, and the practice exam is there to help.